So today I'm going to present a vision more than concrete results. Concrete results can be found at this webpage, which is our research arm at runtime verification. But as I said here, I'm going to focus on the vision, so please try to dream with me a little bit. So what we are after here is a universal truth framework. So what do we mean by that? It's a framework in which any claim made by the framework is verifiably true. That means that the claims come with independent proofs, proof certificates, which are succinct and third-party checkable. So you don't have to trust me or runtime verification or anybody else to check the claim. And now what is a claim? Because that's a very broad word. So a claim can truly be anything that is provable or computable. Okay, if a program executes and gives you a result, that's a claim. The program claims factorial of 6 claims, factorial of 3, claim 6. Or a program is correct. You verify, you audit a program, you get a correctness proof, that's a claim. This program is correct. Or a mathematical theorem. In the end, we are going to reduce everything to mathematical theorems. Program execution is a particular search for a proof of a theorem. So any such claim is going to come with a proof, and this proof is checkable. So you don't have to trust the producer of the proof, you don't have to trust the producer of the claim. You can just check. So how can we do that? So first of all, I think you agree that having this would be amazing, okay? Because we can actually recover, as a special case of this general principle, verifiable computing, what we do with ZK, okay? So how can we do it? Is it doable? And we believe, yes, it is, if we separate concerns, if we split it in two parts. So the first part is I take the claim and let's find a mathematical proof for it. Not cryptographic proof. I make a distinction here between mathematical proofs and cryptographic proofs. Mathematical proofs are these long sequences of steps, thousands, tens of thousands of steps, right? Where everything follows from the previous steps or axioms otherwise. Okay? That's what we've done for 5,000 years, right? Mathematical proofs like that. So let's imagine that we have some AI, some smart brain that takes the claim and finds such a mathematical proof. And we use K for that. That's an open-ended framework, but you can use other tools as well. But let's, for now, assume that K searches for a mathematical proof for your claim. And K actually uses a lot of automated deduction, decision procedures. It may look a bit like AI, but it is a collection of automated tools to search for proofs. Now you have this mathematical proof, which is huge. Imagine that this is like terabytes of proof. It's too big. Okay, so actually program execution, we have a semantics of EVM, for example, in K. You can execute programs, and that execution of a program gives you a mathematical proof, but it's huge. The challenge here is how to make that small. But here is an advantage of very rigorous mathematical proofs. They give you all the details, which means that you can have a proof checker. And I'm not talking about cryptography here yet. Just mathematical proof checkers, which are extremely dumb, very simple. They don't have to do anything intelligent. Just check step by step. Like here that we applied correctly modus ponens at step 248, for example. Right, so these are trivial checks. And indeed, we have a proof checker for the logic that underlies all this, the foundational logic that underlies all this vision, that has only 240 lines of code. So that's it. That's all you have to trust. This proof checker, 240 lines of code, and that can check any claim about any program in any programming language. Okay? However, this proof can be huge. And here is the trick. Let's snark that proof checker. Okay, so let's make that huge proof succinct, get a cryptographic proof of it. Okay, so we get like a cryptographic proof of a mathematical proof. And there are many applications, as I said, of this, but there is one particularly very appealing application, which is a new generation of blockchain. We can think of it as the blockchain of truth, where everything you put claims in particular executions of programs like transactions, as we know them. But all of these actually are checkable, as I said, independently by third parties. You can write smart contracts in any programming languages, but you don't have to be stuck with one particular programming language for the blockchain. And the code will be executed only once locally, and then you generate the succinct cryptographic proof. And any claim comes with this, generically speaking, proof, but it's really a combination of two proofs, a mathematical proof and then a cryptographic proof of it. So it's a proof of proof. So very briefly, what is K and why we have it? This is a framework that took birth in the world of programming languages and formal methods and formal verification for semantics, and where we have such a picture that we have lots of languages, and they are being created, more languages as we speak, and lots of tools for them, and we use the tools for various purposes, like execution of programs, VMs, analysis of programs, formal verification. So all these tools have reasons, and it ends up that these combinations of a language and the tool for a language are very complex systems in themselves. And this state of the art came with two pain points, one for developers and one for users. For developers, basically you have to redo a lot of work. You have to implement model checkers for C, Java, Solidity, symbolic execution engines for each language, or the other way around, for one language, lots of tools, there's a lot of duplication, a waste of talent. So that's for developers, pain point for developers. But for users, also we just have to trust all this. These are amazingly complex tools, and we just have to trust them. At least until blockchain came, and now people are more inquisitive. They want to know why these things are correct. So, well, when we created K, we had in mind both of these. First, for developers, we wanted a framework where you basically plug and play your language. If I want a model checker for Solidity, or a symbolic execution engine for Solidity, I take a semantics of Solidity, I define it, I plug it into a framework, and I get a semantics. I don't implement a symbolic execution engine for Solidity. Okay? I define Solidity, plug it in the framework, I get a symbolic execution engine for it. Now for users, the benefit of a framework like K, but other frameworks have similar properties, is that everything it does ends up being a theorem, actually, and a mathematical proof of it. Even though it's not explicit, you can extract it. It's there. Okay? And that's what we are putting lots of effort into, how to extract this evidence, these mathematical proofs. So basically, all these things on the right of the image here, they come with, they are basically theorems. Under a certain mathematical theory, something holds, and then K gives you a proof for it. K is a very complex system. Some people said that this could be the most complex, actually, formal methods system out there. It has more than 500,000 lines of code in 4 different languages. It's complex, so why should you trust it? Well, you should not trust it. We keep finding bugs, actually, in K as well. But that's why we try to generate proofs, mathematical proofs for everything, from everything that it does. And that's how matching logic, as the foundation of K, took birth. And it turns out that it's more general than what we needed. That usually happens with things that work. So it can serve just as well as foundation for Coq, Lean, and other frameworks, in the sense that basically everything that these frameworks do, you do proof of Coq, Lean, or K, you can desugar it or shallowly embed it into a proof using matching logic. Okay? In terms of expressiveness, matching logic is a variant of second-order logic, if you really want to look at details. But what's different about this logic compared to logics of other logical foundations is that it's extremely small. And to the right, I have the entire logic. There's the entire matching logic, okay? All the proof rules of the logic. And again, everything that you can do with K, Coq, or Lean can in the end be desugared into a Hilbert-style proof using the proof system to the right. And so that's the idea. Now, let's go further. Let's try to implement it. So we looked for various formalisms in which you can implement this. So first of all, how to express proofs and how to implement them. It turned out that metamath was the best that we could find so far, In case you are not familiar with MetaMath, strongly encourage you to take a look. It's a wonderful system. So it allows you to define mathematical theories and proofs for theorems in these mathematical theories using a very simple language. MetaMath itself as a language has more than 20 implementations, all of them just a few hundred lines of code. There are even FPGA implementations. We define matching logic in MetaMath, and that was only 240 lines of MetaMath. Okay, so matching logic, this logic that can check any proofs, right, of any claims, has 240 lines of code in a language that itself has 20 plus implementations, all of them just a few hundred lines of code. That's the trust base. Okay, compare that, for example, the trust base of a system like Coq, which has several thousand lines of OCaml, so you have to trust those, then you also have to trust the OCaml compiler. So that's why it was very important to us to find very simple logic system, MetaMath, feasible. And while we were doing that, we started collaborating with Andrew Miller and his student Bolton, who was doing an internship at RISC-0. And then we said, hey, actually, we can SNARK this proof checker. It's only 240 lines of code. Let's write them in Rust on RISC-0 and see what we get. And it worked. We got the first prototype. Now working on more advanced versions of it. But basically, this turned into a collaboration with Andrew's group and with RISC-0. Tim Carstens, is he here? Oh, hi, Tim, over there. All right, so we are still waiting for Tim to make the whole thing work, the recursive SNARKs and all that part. But once that works, right then, we actually have a way to produce zero-knowledge proofs, certificates for any mathematical proofs, in particular for any computations, any claims of any kind. All right, and now let me wrap up the discussion. So the vision here is that everything we do with programs and programming languages end up being some sort of tools of one form or another, and these tools, when instrumented properly, can in the end produce mathematical evidence, mathematical proofs, not cryptographic, mathematical proofs for whatever they do, and then we can snark those and get cryptographic proof for everything. And we get this picture, right, where if we can prove something, we get also a certificate attached to it. Okay, so the vision here is that instead of going inside a VM, let's say EVM, instead of going inside a VM and implementing a SNARK version of the virtual machine, let it do what it does and make it log enough evidence of what it does in terms of correctness, of mathematical correctness of what it does, and observe from above the execution with a snarked proof checker. Observe and snark that evidence. It's a proof of proof. So that's the vision. And I'm done. Thank you.
So I actually have a question first. So maybe for those of us cryptographers out there, so usually you have an instance of witness, right? So how does what does the proof checker take in here? Like, does it relate to the instance of witness at all for the relation, or is it something else that you're taking in, as your input to your mathematical proof? Because it terminates it's a P computation, right? So, but like in ZK we're doing AMP relations. Like how do these two things relate?
So I'm not sure I understand the question. Can you make it more succinct?
Going back to the example of ZK VM, right? So
yeah.
There's some input that you give it, right? So let's say that you fix the bytecode. There's an input that you give it, and there's execution trace, right? That corresponds to correct execution.
This execution, like here, so with the EVM semantics in K, when you execute an EVM program, you get the log, which would be this mathematical proof, which can be very long, which states step by step which semantic rule of the language you used, under what substitution, under what instance. And step by step, it gives you the entire execution, but at the highest level of detail imaginable.
So yeah, the execution trace is usually in the witness. So we're saying that basically.
That's the witness, yeah.
So you're taking in the execution trace as input.
So there are two tools here. One is K, which generates these witnesses from the instrumented tool. Okay, so you have to instrument, if you want to work with an existing interpreter of EVM, you have to instrument that interpreter to produce this log, this very detailed mathematical proof. And now, the second part, which is the proof checker, will take that And ideally, you pipe them, so you don't have to store that huge log. Pipe them, and that checks every single step, according to the semantics of EVM, according to the logical consistency.
I guess I'll take my question offline. Still confused. But any questions from the audience?
So it sounds like you run K to produce kind of like the trace of the program, right, or something like that, and then you have this matching.
SNARK proof checker.
So the proof checker is like kind of takes this like trace,
Yeah.
and then runs like an interpreter kind of thing, or like
Yeah.
to create the proof.
Yeah.
So can you talk about a bit more about the structure of this trace and how that would fit with like using K normally? Like, do you normally just like run K on an input to produce this and then run the matching thing to
So
K
is a collection. K is a collection of tools. Okay, so K can generate interpreters, semantics-based compilers, model checkers, deductive verifiers. So you use K for different purposes for your language. You plug your language and then you have all these tools. But in all cases, all these tools can be instrumented to generate an actual mathematical proof of what you just did according to the mathematical theory of the programming language, which you call a formal semantics. So you have the formal semantics of the language, that's the trusted, these are the axioms. And then everything, even a program execution, that becomes a mathematical proof of factorial of 3 equals 6 with the implementation of the language. Right, so that generates this long proof. Mathematical proof, I have to keep distinguishing mathematical from cryptographic proofs. This long mathematical proof, which is like a log, but is the ultimate log. It's a super detailed log, going down to the axioms of the programming language. I don't care about the implementation of the language, because I'm going to execute it. Actually, the EVM implementation of EVM, the KEVM implementation is pretty efficient if you execute it locally. Execute it locally, but it generates a proof for you, mathematical proof. And then you snark that with a proof checker.
So you're generating essentially like a long list of constraints or something from the semantics that you wrote in K, and then you kind of check that these constraints all match or something.
No, so there are no constraints. I mean, K may use constraint solving inside, and it does in many places, but ultimately it gives you this sequence of mathematical steps. This gives you this sequence of mathematical steps, which may have been resulted from solving constraints internally. But I don't care about those constraints at this moment when I go to the next level. At the next level, we have now just a SNARK proof checker, which may have its own constraint solving and so on in order to do this checking. But it's a very simple program. It's an interpreter of mathematical proofs.